The most important thing I want you to get out of it, which will become super relevant later in the semester, if the computer would link up nicely. Oh, wow. The whole thing seized up. There we go. Maybe? Right here. When we're talking about all of our calculations, our measurements, all those fun things, it is a number, which nearly everybody writes down, which is great. But a number is utterly meaningless unless you have a unit associated with it. So I can say 6, and that doesn't mean anything. Okay? I would have to associate a unit with that. Well, the unit actually has two pieces as well. It has what I reference as the measurement unit and the substance unit. So I can say 6 feet. Right? That has a little bit more meaning than just 6, but it's not perfect, right? I could add some more information to that. Because if I said 6 feet is how tall my 2-year-old is, that's a little bit shocking. But if I said 6 feet is how tall I am, that's a different interpretation. Right? So when we're thinking about our measurements, we need to include our number, the measurement unit, and the substance that it's tied to. In this particular unit, the substance doesn't become as relevant as it is in the next unit. So really what I want you to do is when you're writing down your numbers, try to include the substance in everything you do. Okay? Get used to that process so that it improves your odds of getting it correct in the next unit.
Is that like when it's with the state too? The gas,
You don't have to get a specific estate, but the more information that's associated with it, sometimes the more relevant, and it depends on the question. Okay? So if we think through the measurements we've really got 4 categories: distance, mass, volume, and time. What unit might you associate with distance? Feet, okay? Because we're American, but of course we don't work on the American system in science. We shift to meters. Meters might be an odd one for distance because how often are you going to work with something that's a meter long? So now we're going to kilometers. Okay, if we think about it, a meter-ish, right? When we're talking about the chem lab, does that look a distance that makes sense for us to be measuring? Probably not. We'll probably be in a smaller unit. That's where we could move to centimeters or millimeters or even smaller. Okay, mass. How would we measure our mass? Grams. Okay, volume. Milliliters. Okay, and then time? Seconds. Okay, or minutes. Most of our chemical reactions are happening on the order of seconds or less, so minutes is way too long for us. Okay, why? Think about moving into lab. If everything was on a minute time scale, that would be a very long, slow lab. Instead of being 240 minutes, we're going to be looking at, or 2 hours and 40 minutes, we'd be looking at maybe 4 or 5 hours per lab. Okay, so we're on that second time scale. Almost all of these are pushed into the metric system, which is what we just kind of addressed. We picked units that were metric based. Okay, so we've got our symbols. These symbols, or the textbook refers to these as the basic unit. Okay, I like to refer to them as the core unit. I have a problem with basic because it introduces the word base, and the problem with base is if you think about the base, where is it? At the bottom. And I don't want you referencing these necessarily going to the bottom. These are core units. They're the interior of it. So when we think of our core unit, we get meters, grams, liters, and seconds. Okay, what also makes this interesting is gram is actually not the basic unit. Kilogram is, which is kind of a bizarre one. Okay, so think of them as core units. These are the inner piece, if you will. So if we wanted to scale up or down, we could adjust these. For instance, if I want to look at a large distance, I don't look at meters, I look at kilometers. If I want to look at a small mass, I don't look at grams, I would look at milligrams. Okay, so we can append a prefix that holds some meaning behind those units or with those units to change their scale a little bit. Okay, so measurements with uncertainty. Here we go. Where's that arrow located? Between the 0 and the 1. So that is true. Do you have more information than between the 0 and the 1? Yes. Okay, between 0.7 and 0.8, zeros out there, so we could say our measurement would be 0.75. Okay, within that, that 5 is a guess. I don't have any markings to tell me exactly that it's 5. The 7 is an absolute truth. So every time we take a measurement, we have to report the absolute truth and 1 decimal as a guess. Okay? That 1 decimal gives us more information than if we just left it at 0.7. Okay? This is where Sig Figs are ultimately coming from. It's coming from taking that measurement and interpreting what we see. Okay? So in this case, we get 2 significant digits. Okay? What happens if we change the scale a little bit? And instead of it being at 1, it's now up to 1,000. Now where's our marker? 750. Okay? Where did we guess? We guessed at the 5. So with this ruler here, we can again see that we have 2 sig figs. That 0 is no longer, or is not significant, because adding that 0 as a significant digit means that I know it is a 0. I don't, because the markings don't allow me to guess that. So it is 2 sig figs. This brings in the issue with zeros. Okay? If that 0 is not significant, then can I just delete it? Why not? Then I'd go to 75 as opposed to 750. Okay? So the 0 is an important number to include, but it's not acting as a number. It's acting as a placeholder. It's telling me where to put the 7 and the 5. Okay? That brings in our issue with our zeros, and we have to be very careful when reporting our numbers so that it is clear to everybody else what device we used. If I write 750 decimal point, that says 3 sig figs. Okay, that changes the meaning. So that's why we have to be careful with our sig fig rules and use systems that make as much sense as possible so that we don't have to have the device with us at all times. Okay. How else could we go through and represent this? We could avoid sig figs altogether, and we could say it's 750 plus or minus 10. Okay. That allows me to know that what I'm looking at is accuracy out to the tens place, because that's what that plus minus is. But do I really want to write plus minus with a number after it for every single measurement? No. This is why sig fig rules come about, is to help us minimize the amount of extra specification we have to go through and do. Okay? You should always append that information, because it is more precise to include that. Okay? We don't. Okay? So, significant digits, when I talk about it, there are 3 rules, and only 3 rules. If you read the textbook, they go through 5 or 6 rules. Okay? And it's ultimately because sig figs can be confusing. And so where I feel this kind of historically came about was they needed some way to accurately represent sig figs. And so they created a rule, then realized there was an exception. So what did they do? They created a new rule. Instead of going back and reflecting on what actually requires for the rules, they kept inventing rules. Significant digits as rules that you see in your textbook, be it a chemistry textbook, a physics textbook, a biology textbook, all of those sig fig rules were not created by a scientific body. They were created by the U.S. Testing Association, because they were trying to come up with ways to standardize test results nationally when it came to scientific reportings. Right? So those rules that you are seeing aren't based in a scientific system, they're based in a testing system. That's why we have a little bit of issues within them. Okay? So these 3 rules work, and they work all of the time. You don't need 5 rules outlined by the Testing Association. Okay? This is in theory a review slide, and you should be able to identify all the sig figs within those, right? Okay, so prove it. So what's the difference between 5 and 6? They both have 2 sig figs. Okay? So why the 0? Yeah, my pen's being uber sensitive today.
Some people
Fine.
write it as a placeholder to draw attention to the decimal point.
If we write that out, that decimal point is kind of obvious right now because my pen's working out. Most of us write in pencil. When we write in pencil, we make the decimal point by just a quick jab. Okay. Oftentimes that decimal point disappears. So that as 0.12 feet could very easily become 12 feet. If we drop the 0 in front, you'd be like, why did I write a 0 in front of 12 feet? That's kind of silly. That pause is just enough time to hopefully call your attention to the decimal point. I call that a leading 0. It's exceptionally useful to include for that reason. It holds no other meaning than to draw attention to the decimal point. Okay? So, for the remainders, for 4, conveniently, there are 4 sig figs. Okay, questions about that one? Should we walk through it? Sure. The 1, 2 are significant. Because there's a decimal point, we'd be using rule 3. This preceded has been getting me into trouble. I need to make it a left-right thing because I think that language is less confusing. It needs to be immediately to the left. Where people will then start is start looking at that rightmost 0, okay, which is fine, okay, thinking about logistics and just anywhere to start. Except when you read, how do you read? Left to right. So by starting at that 0, you're actually running counter to your entire training for how to read. Okay? So don't do that. Start with the leftmost 0 and look to the left. What does it see? A 2. Okay? And I would argue a 2 is wrong, but in a weird way. It's a significant digit. Okay? Because it is a significant digit, what is that 0? It is a significant digit. Now I move to the other 0 and I look to its left. What does it see? A significant digit, which makes it significant. 4 significant digits. Okay? We move to 7. 1 and 2 are significant. We do have that decimal point, so we run the same process. We look to the left. What's to the left of that 0? Nothing, which means that 0 is not significant. We move to the next 0. What's to the left of it? A not significant digit, which means not significant. We only get 2 sig figs.
But isn't the decimal like a significant digit? Because,
The decimal point is not a significant digit.
well, yeah, but if you put that in a measurement, you needed something to determine that the 0 was there.
You need a placeholder to tell you where to put your first significant digit. Yes, that 0 is not a significant digit. It does hold meaning. That meaning is a placeholder, saying don't put a number there. For the same reason that 0 in our 750 was necessary to make sure the 7 went into the hundreds place and not into the tens.
Okay.
So it's not that it doesn't hold meaning. It does hold meaning, but it's not meaning as a significant digit. It's meaning as a placeholder. Placeholders don't count as significant digits. Okay. We move to 8. Those first 2 zeros are going to have the exact same issue. No significant digits to the left. The 1 and the 2 are significant. When we look at that last 0, what do we see to its left? A significant digit, and we get 3 sig figs. Cool? Okay. How many quarters are there? So right away we encounter one of the issues with this slide is that we have a different ability to count, okay? And when we start to count to really high numbers, we start to lose track of that precision in our counting ability, okay? Because we already heard 6 versus 7 for answers on this, okay? Generally, when we're considering counting, less than 10, we're pretty on point, and we don't need to worry about kind of a precision behind that. Okay? So we could say 7 quarters. How many significant digits is that? 1. So if you're saying 1 significant digit, then that could have been 6.9 quarters. Is 6.9 a valid answer for that? No, so it's not 1 significant digit. 2 significant digits. So 6.09 would have been a valid answer. Or if you're balking at that one, we could go 6.99. No, that's also invalid, right? So, how many significant digits? 0. There's nothing significant about this. So you have no meaning. When you counted out 7 quarters, that could have been 7, that could have been infinite, that could have been negative quarters.
I don't know.
I know where you're going. It's a right idea. You just went the wrong direction. It's not 0, it's infinite. There are an infinite number of significant digits in that quote-unquote measurement. Okay? There are exactly 7 quarters, which means it's infinite sig figs. There are zeros after that for an infinite amount of places. That would really suck to have to write out all those zeros. Okay? So that's why we just specify it as 7 and we accept it. Okay? This works out nicely for something that's an easy counting system, but where this typically shows up is in other places. Okay? Those other places being 1 foot equals 12 inches, right? Is that true? Yeah. How many sig figs?
Which one?
Take your pick, because believe it or not, it's the same answer. It's infinite. This is a definition. Okay? Because it is a definition, there are exactly 1 feet in 12 inches. I know I said that weird. Don't worry about it. Okay? Those have infinite sig figs. That comes important when we're trying to deal with conversions, because those aren't measurements. That is a definition, and so it comes with infinite significant figures attached to it. Okay? There are other places where these kind of systems come about, and you would just have to know that they're definitions. Sometimes those definitions are obvious, sometimes they aren't. Okay? Kind of makes sense? Okay. So, why do we care? Well, what happens if we add these things up? Okay? If we entered that into a calculator, I add a little bit weirder than everybody else does in the world. I would get that for an answer, right?
That was last time, they already know it.
Dang.
You do it that way.
It's got the answer.
That's right, but like, they already know it, or did you just do it like?
I won't reveal my tricks. So if we go through and look at that, what happened? And when we add that all up, that is the correct addition. But is that what I'm allowed to report for this addition calculation?
No.
And it turns out no. Okay? And the reason has to do with these extra places. Okay? In that calculation I ran through and did, I assumed that that was a 0. Okay? Do I know anything about that place? No. So that could have been a 0. It could also have been
1 through 4.
1 through technically 4 because of rounding, but let's just push it to the extreme. It could have been 1 through 9. Okay? I'm doing that exact same thing down here. Okay? So when we run through the calculation, we could have had either of those options. Okay, this one gets a little bit trickier to pull off in my head, but let's see what I can come up with. We would get You're revealing all of the secrets.
You do that yourself.
Okay? Are those numbers different?
Yes.
Yeah. Okay? Where those were 9s, it drastically changes the end result. Where did it change the result?
Decimals?
Where in the decimal? In the 10th place was where it first appeared. Okay? Go to our addition subtraction rule. When dealing with addition subtraction in Sig Figs, the result is only as precise as the least precise place. That precision means where did I start to lose value? Okay? When did I start guessing? Okay? If we go through and look at our numbers, for that first number we guessed at the 3 in the 10th place. For the next one I guessed at that 2, which is the thousandths place. And for the last number I guessed in the millions. Thank you. Okay? Where's the least precise place? The tenths. Okay, the millionths, I'm guessing at the millionths place, which means I know about all of those other values. Okay, those are all guaranteed values. I know what they are. And in fact, everything in front of the decimal point are also guaranteed values. I know those are all zeros. Okay? So when we look at this, the least precise place was the tenths place. The result is only as precise as the least precise measurement. Our least precise measurement is this first one, tenths place. Go through when I do the math. Where did it vary? At the tenths place. This is why when we do addition subtraction, we can only report to the tenths place. That's when we're going to start guessing. Okay? Which means for this addition, my answer has to become 115.6. Okay? Some people get confused with the red one with making all those 9s. Remember, those were all guesses. We don't know those, so we could cross those out. We just enter the numbers as is into the calculator. Because we have that meaning, we'll include all of those numbers. We don't get rid of them. We include them in our calculation. The calculator spits out 115.63362. Okay, my guess was that tenths. There's my 6. Okay, should that 6 go up to a 7?
No.
No, why not? That 3 is a small number. We wouldn't round up in that case. Okay? I did try to pick a number that avoided dealing with the rounding question altogether. We'll look at that in a second. So our answer becomes 115.6. 115.6 grams. Okay? So when we do addition and subtraction, we have to be aware of our rules for how to do this. The addition-subtraction rule gets rarely used in almost all of our calculations. Okay, because it is rarely used, what happens with that rule? Most people forget it and screw it up. Okay, because most people forget it and screw it up, where do we see that rule show up? On the tests. Okay, so make sure you know that rule because it's important. Okay? Questions about that? Joe, it looked like you had some hands.
You kind of explained it with the second part of it, because I was thinking that it should have been 7 due to rounding.
Rounding, but yeah, we don't round up, at least not yet. We do have to round eventually, just not yet.
Okay.
Okay, is that hand?
I bet it is wrong what I'm trying to say, but wouldn't you say 150 will be the answer because you have 3 Sig Figs on the second one?
Nope.
Am I wrong?
So I know where you're going with that, which is the next step, multiplication division, saying how many Sig Figs there are. So I'm using some very key kind of phrasing here, and we'll reference this again. Okay, I'm saying least precise place, okay, not the number of Sig Figs. The number of Sig Figs is a different rule. So if we looked, the number of Sig Figs is 3 here. I've got 4 here. Okay, so number of Sig Figs does not factor into addition subtraction. Only the precision factors into addition subtraction. Okay, but that's a nice segue into the next concept. There are other mathematical operators like multiplication division. When we move to multiplication division, our rules for tracking significant digits changes. Okay? So now our result, and this is, I shouldn't be using precise, the result is based off the fewest significant digits. So if I were to calculate the area of this square, what do I need to do? Rectangle. Length times width, right? Okay. And I would then get the area of that square. Okay, so I could run that out. Calculator spits out 33.488 units squared. What should I report as my answer? Okay. If we were to use our addition subtraction rules, we might report out 33.4, but now 5 because of that 8, right? But we don't use addition subtraction. Okay, we aren't doing addition subtraction. We're doing multiplication division. In a multiplication division, it deals with the number of Sig Figs. So I would go back and look at my numbers. 7.28 is 3 significant figures. 4.6 is 2 significant figures, which means I can only report 2 sig figs. Okay? Again, why? Okay? In the case of the 2 sig fig one, okay, that could have been 4.69 to get our third sig fig, so that we would align that appropriately. So if we go through and run that calculation, what happens? It changes. Okay? Where do our numbers differ? In that ones place, right after the number of sig figs. Okay? So our multiplication division actually matches just like our addition subtraction when we look at examples on where that precision is coming into factor. Okay? So that bottom one was again an example, so we can cross that out. Our calculator spits out that big trail of numbers, which, if the multiple choice test is written correctly, guess what? That number shows up on your test. Okay? So if we were to write a multiple choice question here, we could say A, 33.488, B, 33.4, C, 33.5, D, 33. And E, I'm not creative enough. Okay? What makes this challenging is that if you just run the calculation according to your calculator, you say A, you didn't take into consideration sig figs, you're wrong. If you said B, what did you do? Okay, you didn't round. You were using the addition subtraction rules. You said it could only go to the tens place, great, but then you didn't round. If you said C, you rounded, but you also took into consideration the addition subtraction rules. Irrelevant. D now becomes the correct answer because it's using the multiplication division rules and we didn't have to round. Okay? This should be a warning flag for you to make sure you know your rules because all of your answers make sense. You see that? Okay? That's a proper multiple choice question. Okay. What if rounding? The rounding, look at that first non-significant digit. If it's less than 5, then leave your last significant digit alone. If it's greater than or equal to 5, then you can add 1. So if we go through and take a look at that first calculation for our addition subtraction, where's our least precise place?
Hundreds.
The hundredths place. So we report 133. The first non-significant digit would be that 5, which is 5 or larger. So what do I have to do? Add 1, and this becomes 1.34 grams. Make sense? What happens with the other example? 2 sig figs versus 3. 1, 2. First insignificant digit is a 5. I have to add, whoops, that was supposed to be a 1. Add 1 to that one, and my answer becomes 37 units squared. Kind of, sort of? When it comes to sig figs, it's a rule. You have to know the rule and you have to use it. One of the things that I will say is a bit kind of unfortunate with this is that when you run a calculation, there'll be a variety of different sources for where those numbers came from because you aren't actually taking those measurements. You're using numbers off the periodic table. You're using numbers from the questions in an exam. Okay? You could be using a different periodic table. Is the atomic mass for hydrogen 1.01?
No.
Depending on the periodic table you use, it could be 1.008. Okay? It could be 1.0081. What's the difference between those numbers? The amount of significant digits. Has somebody found more significant digits? Yes. And so depending on the system that you're being asked to solve, you may have varying amounts of significant digits going into your question. If you don't account for those appropriately, what happens to your end answer? It's wrong, and it shifts a little out of balance. That shifting a little bit out of balance can be devastating if you were saying using an online homework system, because your number of 1.2 should have been 1.3. You're now entirely wrong. You had all of the math to support your answers being correct, but because your number isn't hitting that error bar for rounding, you get the answer wrong. So be aware of that. And when it comes to the exam, there are two places you get numbers: the question itself and the periodic table on the test exam. Okay? Not necessarily the ones on the wall. Why? Some people may not be able to see the ones on the wall. I can't rely that everybody has equal vision to that. The only thing I can guarantee you have equal vision to is the periodic table in the exam. So when running calculations, you should use that table because that one is guaranteed. Okay? If you use the ones on the wall, it might be the same, it might not. It won't be off by very much. So you can use some approximative skills to nail that down. Kind of, sort of? Yep. And where you saw this might be going is some practice. So, you got 6 questions. Take a swing at them. If you've got questions, raise your hand. I'll come to you. Through these. First one is 3 significant digits. Question 1. These zeros are not significant because there's no decimal place. For them to be significant, you'd have to have a significant digit to the left and to the right. Okay? It's a bit misleading to cross them out because crossing them out makes it sound like you can get rid of them. You can't because they need to be there. That's your paycheck versus that's your paycheck. It's a little bit different in value, right? Okay? So they're important. They just aren't significant digits. We move to the next one. All of those are significant digits and we get 6. Why does the rule change? Because we have a decimal point now. That changes the system. For the next question, for question 3, we want to be able to identify or run the calculation. So the 3 through 6, I ran the calculation, or rather a guest has run the calculations for us. None of those are correct. Okay? Because none of those took into consideration significant digits. You have to address that. So in that first one, for 3, okay, your answer can only be reported to the least precise place. In this case, it's thousandths, hundredths, and thousandths. Which one's the least precise? Hundredths. So I can only report out to that hundredths place. My answer becomes 129.04 meters. Including that one is now wrong because you haven't followed the rules. Does that make sense? Okay. The next one becomes a little bit trickier in my opinion because when we go through and multiply that out, we get 4,538.477701. Okay. Rule changes. Now it's the fewest Sig Figs. So we go through our calculation and evaluate. We've got 5, 3, 6. Fewest Sig Figs is 3. 1, 2, 3. Okay. So where I will get, and then also that is an 8, which means I have to add 1 to the previous number. So I will get people saying 454 because that has 3 Sig Figs. You're right, that has 3 Sig Figs. Did you change the meaning of the number? Yeah. It started at 4,000 and is now 400. That's a pretty big difference. So you need a placeholder 0 in there to ensure that your 4 goes into the proper place. Okay? Where we have to be careful is that we cannot include or explicitly state a decimal point. Because the instant I drop a decimal point, the 0 becomes a significant digit. So I don't want to include that. What was this? Meters cubed. Okay? This is the more accurate way to represent that because we've lost meaning due to that 3 significant digit 3.09. Yes?
Why did you put meters cubed?
Why did I put meters cubed? What happens when you multiply a meter times a meter? The units don't cancel, it becomes meters squared. In addition, subtraction, I just add, it's the same unit. That's why I'm allowed to add them. When we're doing multiplication and division, we'd have to account for that. It becomes meters cubed. For the next number down, we're doing a subtraction. least precise place is going to be the hundredths place, which means I can only report out to that place, yeah? So I will add 1 because that is a 5, and my number becomes 0.03 liters. This is an interesting one to draw your attention to. I started with 4 significant digits and more than 4 significant digits, and I end with 1. When we do subtraction, you will lose significant digits. Okay? That becomes a really big deal. This is saying I'm guessing at that 3. My entire answer here is a guess, which means if I'm going to use that in any subsequent calculation, that subsequent calculation is a guess. That is a horrible calculation to run. This is why when we're doing volumes, we want very large differences in those volumes so that we can maximize the amount of significant digits. If we have a very small volume change, it results in a number with very few Sig Figs, and we end up guessing for our entire calculation. You saw this with the density lab. Your volume change was so small that your entire density calculation was based on a guess. Go figure, you were wrong. Yes?
So you wouldn't add a 0 placeholder for that?
There's not a 0 placeholder to add. If I add a 0 there, with that decimal point, all I need is something to the left. Both of those would be significant. That means 2 Sig Figs. Okay, or I'd have an extra value, and I'd be reporting to the thousandths when I've only got to the hundredths.
Right, okay, I see.
Okay. Last one, division, 3 Sig Figs, 454. My answer becomes 0.0454. No need to round. What happens with the units? Grams over centimeter cubed. Okay? The units don't cancel. I just get grams over centimeter cubed as an answer. That would be a mass over a volume, also known as density. I know where you're going with that. We haven't addressed that yet. How important are Sig Figs? If you're trying to be a scientist or an engineer, they become very critical. There are arguments that we've had space shuttles explode over Sig Figs because someone wasn't tracking them appropriately. I read an article a little while ago that I did not check sources on, so who knows how valid it was, but saying to flying to Mars, you needed to know pi. How accurately did you need to know pi? To 20 decimal places. If you didn't have that level of precision in pi, you miss Mars. Okay? That's a pretty big deal, particularly if you're the astronaut flying there. Okay? So Sig Figs become very important with very large distances and very small things. In chemistry, we deal with a lot of small things. That's why Sig Figs become important. Okay? If you have to take 151 or 152, it's going to be important for you because depending on your instructor, they nitpick Sig Figs a lot. Okay? So you have to be careful with that. What's that? I do not teach 151 and 152. I don't like Sig Figs. Okay?
I was hoping that you were my teacher, so I didn't have to.
Yeah, no. When I teach those, I have to get nitpicky on it. Okay? The other thing that becomes problematic, I already addressed. Where are you getting your numbers from? Depending on where you get your number from, you have varying amounts of Sig Figs, which means you have varying levels of precision in your answer. If you're looking at an online homework system, there is one answer. They usually put in a little bit of rounding error, but depending on where you got your number from to source that question, you could very easily end up with a wrong answer, even though your calculations are correct. Okay? So you have to be very careful with Sig Figs. It shows up in our textbook, so if you're looking at the answers in the back of the back of your textbook for calculations, you may notice there's some weird rounding issues. Again, where are you finding the numbers to source for that question? Okay? Depending on where those numbers are found, you can get slight variances, and it can be a pretty catastrophic difference for an answer. So be aware of that. Okay. If you want the answers, as Alyssa was already trying to hint at, the answers are at the bottom of the slide. Okay, I believe I actually took into consideration all the Sig Figs for those. Okay, so I would recommend putting it on one slide. So here's all of our Sig Fig rules on one slide. Okay, you can take a picture of it. You have the slides. You have them. Okay, if you're not going to go dig into Canvas, that's fine. Take a picture. Okay, but you literally have the slides. Okay, we good? Okay. So simplifications. If I ask you to write that out, okay, you don't have to write that out. I see you, Tyron. That's nice, but you don't have to. Okay, or enter it into your calculator. You might be that's tedious, right? What's the shorter way to do it? 4 to the 6th power. So we can take advantage of exponents to say repeated multiplication. Okay, we have addition, subtraction. What's repeated addition and subtraction? Multiplication. What's repeated multiplication or division? Exponents. Right? So we can scaffold through and see those scaling factors. They can shortcut the amount of work that we have to go through and do. Okay, so you could see exponents pop up. Okay, in fact, you will. 2 common exponents, you'll see squared and cubed. Why do we call them squared? When I look at the area of a square, what am I doing? I'm multiplying 2 sides. Okay, there's the square. When I look at a cube, I'm multiplying 3 sides, length, width, whatever, height. Okay, so we're getting that cubed value come out of that. Powers of 10. We'll see the powers of 10 show up. Okay, they are ways that we can take really large numbers and convert them into powers of 10 so that we don't have to deal with all of those zeros. What are all of those zeros? What's the point of powers of 10? Really small and really big, but more importantly, all of those zeros are placeholders, and that's why we're going to powers of 10. So we're trying to disambiguate the 0 and say the 0 is now a placeholder versus a significant digit. If it's a significant digit, you got to write it. If it's just a placeholder, we can come up with a shorthand to hide it. Okay, that's the point of our powers of 10. This is going to immediately show up when we move into scientific notation. If we've got these really large numbers or really small numbers, what I'm trying to do is get rid of all of those placeholder zeros. I don't want to have to write them all out. So the method, okay, shown down below, our first significant digit in the ones place, decimal point the rest of our significant digits. Then we'll multiply by a power of 10 to get us to the appropriate number. I have finally freaking updated this slide, which makes me so happy with the rules at the bottom for step 2. So let's take a look at that first number. 4 is my first significant digit, decimal point, 063. All of these zeros are placeholders, so I can ignore them. Multiply by a power of 10. This is where things can become a little bit dicey, because now what I'm going to do is show a decimal point. There was an implied decimal point in this number. Okay? So starting from that implied decimal point, how many places did I have to shift? I should have been counting as I did that. 1, 2, 3, 4, 5, 6, 7, 8. Because that's where I put my decimal point. So I went 8 places, so this is 8. Okay? I have to decide on how big that number was. Is that a number larger than 1? Yes. Which means the sign for my exponent needs to be positive. So we're talking about big and small. It's in reference to 1. Do I need to show the positive? No. Arguably, if we look at life, we should probably show the positive more, but we don't. Okay, a little optimism there for us. What happens if we move to the next number? 1.16 times 10 again. This time the decimal point was actually shown. 1, 2, 3, 4, 5, 6, 7. Again, I shifted it 7 places. Was that original number large or small? Small, so -7. The negative I will have to specify because it's changing the direction I'm moving. Okay? You may hear reference to shifting the decimal left and right. I think that's a bad idea because depending on which way you're going, left and right changes, right? Okay? Which may sound a little bit weird, but if you're going from scientific notation to the expanded notation versus expanded to scientific, it switches things around a little bit. So that's why we have to be a little bit careful with it. Okay? So this is an interesting one. We've got these two systems. Okay, and we're just going to pick that top number. Okay, measure the distance to the moon. There's a number. When I took that measurement, I measured it using a 1 meter stick. How many significant digits are there? Okay. How many significant digits are in the number as reported? As reported, for those zeros after the 3 to be significant, what also needs to be true?
It has to be a decimal.
I either need to have a decimal point specified, or I need a significant digit somewhere to that right. Are either of those conditions satisfied? No. So the number as reported has 4 significant digits. But if I take this measurement using a 1 meter stick, what does that mean? How does that change the number?
There's an implied decimal.
There's an implied decimal is one way to approach it. If I'm using a 1 meter stick, that 0 is significant because I'm using a 1 meter stick. So to get a 0 in that 1's place, it had to be exactly 0. Okay? So I've reported the number horribly wrong because I should have included a decimal point. Now I've accurately reported the number according to the device I've used. Does that make sense? So that was actually a clear example. So let's really muddy the waters on this one. Instead of using a 1 meter stick, I use a 1,000 meter stick. Just work with me here. Okay? If I'm using a 1,000 meter stick, can I measure a meter? No, because my stick is 1,000 meters. So that 0 at the 1's place, I don't know. How about at the 10s? Hundreds? Thousands? Yes. Which means that 0 is also significant, yeah? So now my measurement has 6 significant digits. How do I report that? Okay. Because if I put the decimal point here, these zeros become significant. They are not significant. Okay. If I put the decimal point here, now what's the problem? It's a smaller number. I've changed the meaning. I've gone from being 406 million to 406,000. That's a really big difference. Okay? So as Rose is suggesting, this is a perfect situation for when I need to use scientific notation. I report a number in the 1's place, or my first significant digit in the 1's place, that's that 4. I report all the other significant digits. Then what do? I multiply by my power of 10. How far did I shift the decimal point? 1, 2, 3, 4, 5, 6, 7, 8. And it was a number larger than 1, so it would be positive. Now when I report that measurement, the precision of the device I've used is embedded in my calculation, or embedded in my measurement. If I use the initial writing, I've lost that meaning. I don't know how to report that information. That is admittedly a small circumstance under which that would happen, but it could. That's why scientific notation comes into play, is to really make sure that we can clarify the difference between those zeros when we're floating somewhere in between. Yes. It's a challenging concept to deal with. Scientific notation allows us to differentiate non-significant versus significant digits in the middle of our number sequence or our number line. Without scientific notation, we can't do that easily. Okay. There are ways to do it, but let's not worry about that yet. Okay? So that's one of the big uses of scientific notation. It allows me to differentiate zeros. Okay? You think you can word it?
No, I think I just.
Think you got it?
Okay.
Okay. Anybody else have questions? Okay. So, the other thing we can go through and do is if we've got these numbers with all those zeros, we may decide that, you know what, I don't want to report all those zeros. I don't want to report powers of 10. Okay? So instead of saying that that number back here was in meters, I could have changed that to be kilometers. Okay? So now I've disambiguated some of that information. I need the decimal point. By switching out that unit. Okay? So I can change the measurement unit. Okay? And this is one of the powers or the beauties of the metric system is we have powers of 10 manipulations that we can make off of our units. Okay? And for those people that think that's kind of silly or not all that unique, how do we shift between inches and feet? It's not powers of 10. Okay? Or even inches to what's our smaller measurement than inches? Shifting out of the English system, right? To go to centimeters. That becomes problematic. Quarter inches. So we end up using still inches. We're just now using decimal versions of it. Okay? So that system has some big, massive flaws that makes it difficult to scale easily. The metric system allows us to scale easily off of powers of 10, and that's a beautiful thing. Okay? That means we have to tie meaning of a symbol, which is our modifier, okay, our prefix on our core unit. We have to know that modifier and what it means as a power of 10. Okay? How often are we going to deal with tetra? 10 to the 12th. We're looking at massive numbers, so that's probably not going to happen so often. Okay? So if we aren't going to use it so often, what does that mean to you? Probably don't have to memorize it. Does that mean you won't be asked questions about it? No, you will absolutely potentially be asked questions about it. Okay? In that tetra scale, though, I will give it to you on an exam, that conversion, or that relationship, or it's in a homework question. And in the homework question, you are expected to go look it up. Okay? So which of these should you actually spend time and brain power to memorize? There's no... So I see where you're going with basic unit. The core unit is something we've already addressed, and you do have to memorize those. Kilo is a prefix, yes. Which of those prefixes should we bother to memorize? Kilo, centi, and milli. Okay? Those three you should have memorized. Okay? And it's going to keep coming up. You should memorize that milli means 10 to the minus 3, centi means 10 to the minus 2, kilo means 10 to the third. Okay? For those people that have had a different memorization system, I understand where you're potentially going with that. The problem with the other systems is they get applied inconsistently when you go through to do conversions. If you memorize these as this pattern, when we start to do conversions, they will always get applied the exact same way. That is the beauty of having it memorized this fashion. Okay? Since you've now committed that to memory, we could now look at some examples. If I wanted to convert 1,200 meters to a new unit, My scientific notation would become 1.2 times 10 to the third meters. What did 10 to the third mean?
The decimal point, 3 spaces to the left.
I did move the decimal point. It meant kilo from our previous thing, and we could write this as 1.2 kilometers. That power of 10 now disappears from my system because it's embedded into the kilo. It simplifies the number that I have to write out. That's what we're doing. Okay, do you guys want to work through those examples?
Yeah.
Okay, I'll give you. So for that second one, we shifted the decimal place twice, so 10 to the second. I'll deal with it in a second, trust me. Shifted the decimal place twice, shift the decimal place 3 times, yeah? Okay. Now deciding the scale. Is this number greater than or less than 1? Less than 1, which means minus. Less than, greater than 1. Less than, minus. Greater than, less than. Less than, minus. 10 to the minus 2 meant centi. So I get 1.2 centiseconds. Some people were like, centiseconds exist? Yes. Any of these permutations exist. That does not mean they're commonly used, okay, but they exist. Okay, and the next one, 10 to the minus 2, still centi, centiliters. Okay, same deal, not commonly used, okay, but it exists. For the last one, 10 to the minus 3 was milli. So we'd get milligrams. Kind of makes sense? So this is allowing us to kind of scale between those different unit systems. Okay, and as long as we're just doing that power of 10 shift, we're allowed to do that manipulation pretty quickly and efficiently. Questions?
Can we just write it in scientific notation?
Could you just write it in scientific notation? Yes and no. What if I asked you what is the number in centiseconds? Scientific notation is not going to work because you're now not addressing that unit. Okay? So the whole process behind this is trying to understand where those units come from and how they manipulate out. Okay? So you have to be able to manipulate at all those different levels.
Can you go to 12 milliseconds?
Could you do 12 milliseconds? What do you guys think? How did he get to milliseconds? Let's try and do the reversal. What does milli mean? Milli does not mean million. Milli meant 10 to the negative 3. Whoa, that was an S. If we're going to move the decimal over 3 places, 1, 2, 3, our number would become 0.012 seconds. Is that what was given? Where did it go? Jiminy, Christmas? So yeah, could you have done that? Yes. That is a valid representation for it. Okay? What I was asking for, though, was trying to get that connection between those. So milli was a valid way to convert that out. Okay? Why would we say 12 milliseconds versus 1.2 centiseconds?
No one uses it.
Common. More people use milliseconds, so let's take it to milliseconds. Why write 1.2 centiseconds? That's coming from scientific notation. Is the 12 milliseconds coming from scientific notation? No, because our first significant digit shows up in the tens place, and it needs to show up in the ones. Does that make sense? So you can convert to any different unit system based off the powers of 10 that you wanted to, and a lot of that is preference. In this case, it was just trying to show that relationship.
So,
Damn it, I just had to advance the slide. What did you say?
with back there, it had went from 1.2 times 10 to the power, so basically when you convert it to the number in the new unit, it gets rid of the times 10 to the power.
Yes, because that times 10 to the power is where you shift the decimal.
Okay.
That's what's helping you to decide where the decimal point moves. Okay, so back to our sheep, we had qualitative and quantitative. So this is really just back to chapter 3. And in chapter 3, what they're trying to address is physical properties versus chemical properties. This becomes a really important thing for us in this new unit because what we're now being expected to do is to look at chemical reactions and decide how do we know we have a chemical reaction. So the physical properties are something inherent to that compound so that when I test it or when that thing happens to it, it doesn't change the elemental composition. A chemical property changes the chemical composition. Okay? So I think the chemical properties become a little bit more difficult to define because the chemical properties necessitate a chemical reaction. Physical properties, there's no chemical reaction happening. Okay? So where this becomes more important for our chemical properties are really our difference between chemical and physical changes. Okay? Physical changes, you're maintaining the chemical composition. Okay? That's not always inherently obvious. The easiest way to think about your physical changes, though, would be, are they reversible? Okay? And in particular, are they easily reversible? Okay? When I boil water, what happens to the water?
It's the gas.
Turns into a gas. Can I easily reverse that?
If you had the heat.
If I remove that heat, what happens to the gaseous water?
Turns back to water.
Turns back to liquid water. Okay, so that's a relatively easy thing to change. Chemical changes, not so easy to do. Okay, if I heat up a block of wood, okay, what happens to it? It burns. It turns, we see a fire. What's happening? The wood now becomes ash. What happened to the rest of the mass of the wood? It combusted. It turned into some other substance. That reaction becomes a difficult one to monitor because what are you reacting the wood with? It's not fire. Oxygen. It's oxygen that you're reacting it with. Why has that become a difficult reaction to track?
Can't see.
You can't see oxygen. Okay, so a lot of our chemical reactions are difficult to track because we can't see them. Okay, so we get a new substance forming in that. What defines a new substance? Well, a change of phase was a new substance, right? When I boiled water, was that a new substance? No. Okay, so there are certain things that are triggers for deciding chemical and physical changes, but every single one of them has counterexamples. Okay? So our evidence for chemical reactions, your textbook lists them out as 4 things. I think it's really just 3. 1 and 2 are the same, a change in phase. Okay? If I go from a liquid to a solid, that is a change in phase. Okay? That is evidence for a chemical reaction. When I take 2 liquids and I mix them together and they become a solid, okay, that was a chemical reaction. Okay, where did the energy go to make the solid? Did I remove it or did the chemicals remove it? The chemicals did it. So a lot of these phase transitions are based off of where did the energy go or come from. Okay? If I'm removing energy, now I'm causing that change. That's on me a physical. Okay? The easier one to look at is phase changes to a gas. Okay? Because everybody understands going to a gas. To go from a liquid to a gas, what do you have to do? Add heat. If I take 2 liquids and I see a gas, but I haven't supplied the heat, where did the energy come from to make the gas? The chemicals, which means chemical change. But if I take 2 liquids, I don't see a phase change, but now I add heat, and I see a phase change. The phase change was due to me adding the heat. That's now physical. So a lot of these processes have to decide on what's causing the change. If the change is something internal, it's chemical. If it's something on the external, that's a physical change. Right? A permanent color change. If I take 2 clear solutions and I mix them and they become yellow, chemical or physical? Chemical. If I take red food dye and I add it to white cake frosting, what happens to the white cake frosting? Turns pink. Let's go with pink first so it's not the same color. Is that chemical or physical? That's a physical change. That was a dilution in the color. One of the things that we said about physical changes is that they're reversible. Guess what? Adding red food dye to cake frosting is reversible. Really hard to do, but it is reversible. Okay? So you can reverse that process. The last one, an energy change is observed. If I mix two clear liquids together and all of a sudden it gets hot, where did the energy come from to make it hot? The chemicals. If I mix two clear liquids and it gets cold, why is it getting cold? The chemicals are causing that energy change. So a lot of this is when I just mix those, let them decide what's happening, and now we observe it. Okay? If I haven't caused that thing short of mixing them, then it's a chemical reaction. Okay? So there's a color change. There's supposed to be an energy change, okay, with the heat. Okay? On deciding chemical and physical, this is where we will pick up with on Thursday. Thank you. We will also look at balancing equations on Thursday. Okay, so please watch that video to get you an idea on what's going on with those.